Hello. In this lecture, we will explain how AES encryption using counter mode works. This is defined in RFC 3686. So, if we treat AES encryption process without getting into the details of how AES actually encrypts the traffic, let's leave this as a black box. AES includes many mathematical operations that is not the point of our discussion. The purpose of this lecture is to understand the process of encryption and decryption. AES requires the encryptor to generate a unique per packet value and communicate it with the decryptor. The way this gets done is as follows. Each packet will have an initialization vector number attached to it. This initialization vector is used to XOR the plain text. So, if you recall when we generated ASCII, assuming that we are using 128 bits AES, the ASCII that gets generated is 20 octets or 160 bits. We use the first 128 bits as the AES key, and the last 4 octets or 32 bits, for a number used once. This doesn't change for the life of this Phase 2 security association. So, the counter mode means that the plain text is XORed with a unique series of bits, or keying material consisting of the concatenation of the initialization vector, nonce and a counter. So let's take this process from the initiator to the responder. The initiator basically splits the plain text into 128 bits blocks for the XOR phase. If the plain text doesn't divide with 128 evenly, the leftover is truncated. Now, the plain text is split into X number of 128 bits blocks. Each block gets XORed with the concatenation of nonce, initialization vector and a counter. This counter increments from 1 to n+1, number of 128-bit blocks. Let's call this concatenation as a counter key. So, the plain text is chopped up. Each block is XORed with the counter key. The outcome of this XOR operation is encrypted using AES using the key of ASCII IDE. The first 16 octets of the ASCII IDE is now used to AES encrypt the ciphertext. You would then have ciphertext blocks C0 through Cn number of blocks matching the number of plain text blocks. The initiator would send the responder the packet which is composed as follows. The ESP SPI, followed by the initialization vector. This would be followed by the encrypted ciphertext, encrypted using ASCII. The recipient gets the packet, it extracts the ESP SPI information from that field in the header. It does a lookup against the Security Association database to get the ASCII IDE that was used to encrypt the data, which would be the same key to decrypt. It also extracts the initialization vector, this is in the clear after the ASP SPI and sequence number payloads. It will get the ASCII for encryption for the initiator and based on this lookup, it will determine also what the nonce is. The nonce is the last 4 octets of the ASCII, which helps the recipient compose the counter key. The counter key is the nonce concatenated with the initialization vector and counter 1 through n+1 number of blocks. Okay, so it will get the ciphertext payload, split it into 128 bits chunks and decrypts each with the ASCII IDE. It will then XOR the outcome with the counter key, getting back the original plain text. The result of the XOR operation would turn out the original plain text or payload that was encrypted. So, one of the main key things to understand is that the initialization vector cannot repeat at all in any Phase 2 communication. The sender is the actual entity that ensures that the initialization vector doesn't repeat. If the initialization vector repeats, the communication can be easily decrypted by an eavesdropper. The RFC left the issue of not repeating the initialization vector a responsibility of the sender of the packet. Now, The initialization vector is a 64 bits value, which means it is a very large number of packets for this initialization vector to roll over, making it easy to meet this requirement. Hopefully this was helpful. We will talk more in the next lecture.